So now we're going to look at doing the same thing in terms of finding a relative minimum or relative maximum, but using the second derivative. So just as a reminder with our last one with the first derivative, we had to think about these intervals and the behavior within those intervals in terms of increasing, decreasing. With this one, what we can do is we can find those critical values and evaluate the second derivative at those points. I'm just going to say it at the beginning here. I really like the second derivative test. Yes, it's a little bit more work to get to the second derivative, but feels a lot more direct in terms of the evaluation of whether it's a minimum or maximum. So what we're going to do is if C is our critical value, we're going to look at the second derivative at C, and if it's positive, that means, remember with the positive second derivative, that's where we're concave up. So that would be making a relative minimum. If our second derivative is negative, then that's where we have concave down. And that would make a relative maximum. And then if our second derivative is equal to 0, then we can't use this test and we actually need to go back to that first derivative test to see what's going on. All right, so our steps. We're going to find our critical values. We're going to go ahead and find the y coordinates at that point. And then from there, we're going to look at the second derivative of those values. And then we can determine whether we have a relative minimum, maximum, or if our test fails. All right, so here we have this nice polynomial. I'm just going to rewrite it again. It helps me to have it rewritten right above where I start taking the derivative. So first thing we're going to do is find those critical values. So that means we're going to take the derivative and set it equal to 0. So that'll be a 3x squared plus 6x, and that's it. Set that equal to 0 and start solving. Let's see, there's a greatest common factor of 3x here, so I can factor out a 3x, which will leave us with an x plus 2. And solving, that means we'll have an x equals 0 and x equals negative 2. And that right there, those are our critical values. So our table's going to look a little different here. What I'm going to do is on the table, it's not going to be intervals. What we're going to do is have the critical value coordinates. So I'm going to go ahead and do x, y. So we have our x coordinates. We know we have an x coordinate of 0 and an x coordinate of negative 2. And to get the y coordinates, we're just going to plug in to our function up above there. So if I plug in 0, that's not too bad. That's going to be a negative 4. If I plug in negative 2, oh, do I want to do that in my head? I don't think so. It would just be you hearing me mumble for a bit to myself while I try to do that. So let's just go ahead and use the calculator to help out. Plus 3 times 4. And there we go. All right, so that's a positive 4. I'm just going to make sure I typed that in correctly. No, I didn't. There we go. 0. Okay, here we go. All right, so we have our critical values, and specifically these coordinates. So these should be making, if we go back to our graph that we looked at here, basically we found these coordinates where we're having these flat tangent lines. So those could be maximums, or they could be minimums, or they could be nothing. It could be this flat spot. So with that, taking that derivative and setting it equal to 0, that's what we're finding with these coordinates. So now what we want to do is we want to evaluate each of those points at the second derivative. So what I'm going to do is, we did this work for finding the critical values. What I want to do is take my first derivative and change it to a second derivative function. So 3x squared, the derivative would be 6x, plus 6x, the derivative would just be 6. So what we want to do is evaluate the second derivative at these points, which is really just plugging in that x coordinate with that second derivative function. And again, all we want to know is if it's positive or negative. So if we plug in 0, that's going to be a positive 6. So we're getting a positive number out. If we plug in negative 2, negative 12 plus 6 is a negative 6. So that's negative. So what we end up with here is concavity. So this is saying we're concave up at this point. And here we're saying we're concave down. Which means concave up looks like this, which means we're hitting a relative minimum. And concave down looks like this, which means we're reaching a relative maximum. And we're done. I don't know, to me it feels like a lot less work than the first derivative test. They both accomplish the same thing, but second derivative, I just like that we're working with a coordinate that we're actually interested in, so it's not as much of a roundabout way. So let's go ahead and take a look at the graph of this and see all of that coming through. So we have x cubed plus 3x squared minus 4. All right, so we're seeing something concave down, and we're reaching this maximum at negative 2, 0, which is exactly what we have over here. Negative 2, 0, hitting a relative maximum, and then relative minimum, 0, negative 4, and it's because we're concave down in there. If we needed an inflection point, we would just look at where this second derivative is equal to 0. They didn't ask us for that. So that process, get those critical values, and then you can get the actual coordinates at those critical values, then evaluate the second derivative at those points. And positive versus negative will give you that general shape, which will tell you whether it's a minimum or maximum. Let's go ahead and do one more since I love the second derivative test so much. All right, so we have our function. I'm just going to write it again. So 3x to the 5th plus 5x cubed. We're going to take the first derivative. So 15x to the 4th plus 15x squared. And we want to find our critical values. So let's go ahead and set this equal to 0. Sorry, I'm just debating. I'm going to go ahead and find the second derivative. Just while we're in derivative mode, I'm going to move the steps a little bit. So 15 times 4 is 60. X cubed plus 15 times 2 is 30 and x. Okay, just get that second derivative done and we'll use it later on. All right, I still want to work with this first derivative because that's where my critical values are. So 0 equals 15x to the 4th plus 15x squared. Let's see, we have a common factor of 15x squared, and that'll leave us with an x squared plus 1. So we'll have this 15x squared equals 0, and solving, like, divide by 15, square root of both sides, which we technically have plus or minus, but the square root of 0 is just 0. So we get x equals 0. Then when we're trying to solve this x squared plus 1 equals 0, so I subtract 1 from both sides, then when I take the square root, I'm going to end up with a problem. We can't do that. So with that, that's not providing me any information in terms of critical values. All right, so I have a critical value at 0, and we would want the y coordinate coming from f of x. So if I plug in x equals 0 here, we would get 0 out. And then I want to evaluate the second derivative at this value right here. So second derivative, if I plug in x equals 0 into my second derivative, we're going to end up with 0. And what we're told to do is that if the second derivative of f of x is equal to 0, our test has failed, or specifically the second derivative test has failed. So we need to go to the first derivative test. So what I'm going to do here is I have to abandon my beloved second derivative test. So we're going to skip that, and we're going to go to our first derivative test to see what is going on with this graph. So we found derivative test. Okay. So the first derivative test, we have intervals, and our cutoff was x equals 0. So we're going to have two intervals. We're going to have behavior from -infinity to 0, and then we're also going to have from 0 to infinity. Then we're going to want a test value in each of those areas. So we're going to grab, how about a -1 and +1 to make that nice and easy. And then we're going to evaluate the first derivative at each of those points. So we're going to go back to this function right here. So if we plug in -1, let's see, those are both even exponents. So that's going to turn to a +1, +1. So it's going to be a +30. If we plug in +1, we're going to get the same thing out. So what's happening here is it's going increasing to increasing. So because that behavior is staying the same, there is no relative extrema for this. We don't have a minimum or maximum. What's happening here is we're going to have something that's increasing, that flattens out, and then is increasing again. So that I can kind of visualize a sketch of this graph before actually graphing it. So this is one where we don't end up with relative extrema, and that can happen. Doesn't feel great, but it can happen. So if we look at the graph of this function, you can see, in fact, we do have this graph that flattens at that 0, 0, and we're going from increasing to increasing, but with that, we're not seeing any minimum or maximum values.